All right, here we go. Introduction to vectors. Okay, so today's lesson will be straightforward if you've done physics before. If you haven't, it should cover grade level physics today. If you've never taken physics, don't worry, this will get you all up to speed here for this. Okay. So we're going to say a scalar is a quantity that describes only magnitude. Okay, examples are 58 kilograms, 200 kilometers, and 180 miles per hour. By the way, after that test, nobody please go when they get pulled over the cops for going too quickly. Don't say that your average speed over the last 30 seconds was slower, because they won't buy it, just so you know. Okay, they look for the instantaneous rate of change. Hope you guys got that from the test, okay? So, okay, a vector is a quantity that has magnitude and direction. Okay, examples are 300 kilometers north 30 degrees east, 180 miles per hour south, 20 newtons down. Okay, all of those things will have direction to them, right? All right, and that's sort of the main thing. We'll be dealing more with directions because it's more precise. That's the main difference between the vector and a scalar. Just to continue here with my definition here before I get on to examples, I'm going to say a true bearing, because the textbook likes this. I use it a little bit, but the textbook uses it all the time. A true bearing begins at north and rotates clockwise. So if you see something that says, my example for this is if I say 5 kilometers at 210 degrees, okay? What that means is you're starting north and you're rotating clockwise 210 degrees. So it's going to be, there's straight north, there's 90, 180, this distance right there is 210 degrees. Okay. What's another way I can call that other than 210 degrees, like using north, south, east, west, using the compass coordinates? What would I call that? And those of you who heard physics before, you should raise your hand right now. Go ahead.
East 40 west, or
30 west. So you can call this is or 5 kilometers south, 30 degrees west. Now, how that comes from is, just so we're all clear, you're pointing south, you rotate 30 degrees to the west. Okay, and you remember never read, try to read, or whatever they call it. Is that what they call it still? Never read, try to read? Compass things. Okay. Yeah. Okay, are we feeling okay with that? That concept, yes? Okay. Let's get into a few more little things here. Actually, one other thing I should put on here. I should maybe put a little, a dot. Is the tail beginning of the vector. An arrow. Okay, so when I'm saying 5 kilometers, you're going from here to here. That's what I'm trying to say there. And as I said, this is going to be a straightforward lesson for those who have done physics before. Okay, it's just a quick reminder. If you haven't done physics and I'm saying something that doesn't make sense to you, Cal, I'm looking at you because you told me you've been taking physics. Okay, right? If any of this stuff is totally mushy, and I'm just picking on you right now because I know that there's about 10 of you that haven't taken physics, you said, please someone stop me and, you know, say I don't understand and don't worry, okay? All right? I'm sorry, I hope I didn't embarrass you, Cal. Everyone knows how you think.
I'll stop you.
Here we go. So we're going to say two vectors are equivalent. If they have the same magnitude and direction. Two vectors are opposite. If they have equal magnitude but opposite direction. I'll get out of the way here for those who can't see. Okay, sorry, Callan, I'm keep on picking on you since you're the fastest person in here. So if I say that Callan runs at 20 meters per second north, 20 degrees east, I am an equivalent runner to him if I can also run at 20 meters per second north, 20 degrees east. Clearly I can't. Okay, right, but go with me here. It would be opposite would be if I was heading in the opposite direction for him. Okay, right, so we're both going at 20 meters per second, but I'm running like this and he's running exactly the opposite way. That's what we're saying. Okay, and we were going to get into this before. If two vectors are opposite when they're added, they should have zero result, right? Because one's pulling in this direction, the other one's pulling in that direction, nothing should happen. Okay, are we okay with the concept of that? That's all we're saying. I'm going to draw a picture to make sure. All right. And I apologize. This is very wordy today's lesson. I'm trying to eat better tomorrow or Monday, I guess. Oh goodness. Remember how I said I'm not a good triangle drawer? Apparently I'm a bad parallelogram drawer as well too. Okay, so that's supposed to be a parallelogram. Go with me here, okay, please. This is why I use rulers. Okay. That's parallelogram, okay? Okay, so let's make a quick list. Can somebody give me some equivalent vectors? Can somebody be brave and try and give me two vectors that are equivalent in that diagram? Assuming again everything's parallel. Go ahead.
The top and bottom.
Good. We're going to label those properly though.
A, B, and B.
Yeah. So we're going to say that A, D. We'll put a little vector symbol above. Is equivalent to BC. Okay. Now there will be an arrow symbol above the line. So again, we're just labeling from the beginning to the end. A goes to D and B goes to C. There's at least another set of equivalent vectors. Can someone else be brave and give me another set of equivalent vectors? Go ahead, Teresa.
A, B, and C.
Yes. AB is equal to DC. Now, just to blow your minds a little bit, I'm going to say that there's more equivalent vectors. Somebody wants to have their minds blown. Chris, go ahead.
Perhaps there's no lines there, but AC to BD.
No, those are not because they're not parallel, okay? So definitely those wouldn't be because they're not parallel. Go ahead.
Would be ABC and ADC.
You're thinking close. The vector's only going to be in a straight line, so we're going to say no for right now. Here's to blow your mind, ready? How about DA, if I go this way? What's equivalent to DA?
CZ.
Yeah. Now you might say, Mr. Sadler, what does that even matter for, okay? Well, we're going to get to proofs and work our way along, right? So they have to be in the same direction, so we're going to count those. With that little piece of knowledge to you, what else is equivalent then? BA and CD. Okay, opposite vectors. Okay, here we go. I don't want to put people down, okay, guys, so I apologize, okay? So just try and be brave here. Raise your hand. Derek, can you give me one set of opposite vectors, please? AD is opposite of CD. CP. So AD goes like this, CP goes like this. Everyone's agreement with that? So the way you write that is AD is equal to negative CB. Because it's a negative, meaning it's opposite, right? The direction is opposite. There should probably be 3 more sets. If I choose a vector DC, Chris, I'm going to pass on you because I think you get this, okay? Okay, someone else, if I say DC, can somebody tell me a vector that is opposite to DC?
BA.
Yeah. So we're going to say that DC is equal to negative BA. Yeah, I wonder if I should do this. Did you guys talk about these things in physics? I have a question for those physics students here. Is CD opposite DC? I'm going to say it is. I'm going to say it would be. Does that make sense logically? Logically? Can I count that? Right?
So CD is opposite of
DC. Right? I think that makes sense to me
yeah.
logically. Do you logically agree with that? There's no argument with that.
CP at first.
It's the same distance but opposite direction, right? And so I'm going to, do you want me to just list many more, or I'll write that one down because there's infinite amount basically that are opposite. So I'm going to say that CD is equal to negative DC. I'm going to say bracket plus many more. Okay, because there's a big list there. Are we okay on the concept here of what we're doing here? Okay. Okay. So basically what we're going to do is sort of do the things that Chris was trying to do, that Teresa were trying to do eventually here, or to make new vectors and get them equivalent and stuff like that. So I like what you were trying to do this sort of thing, and you trying to do this sort of thing. We'll be doing those things in this unit, right? So just go around. All right, I'm going to give you guys do a few questions for me, and then we're going to, I'm going to hit pause in the video. Example 2. Example 2, and this is example 1 really. Is each a vector or a scalar? If it is a vector, please state its opposite. Okay, so I'm going to give you a list of 8 scenarios here. Okay, you're going to tell me if it's a vector or scalar. If it is a vector, I want the opposite. If you need to draw a little diagram for yourself, feel free to do so. That's okay. Is everyone done with this messy board here? We're all good. Anyone still need this one? That's a no? Okay, so this is, I'm going to just try and spread this out to give me some room here. So it's going to be A, B, C, D, E, F, G, and H. And then I'll hit pause in the video. Okay, A says a ball is rolling on the floor. At 2.5 meters per second. We're going to say Austin. Happy birthday tomorrow, Austin. Just pushing a crate. course. 215 degrees west. A sound has intensity 50 decibels. The train travels northwest. At 115 kilometers per hour. Spare blocks travels 700 meters at a bearing of 120 degrees. The box has weight of 84 newtons. The high temperature yesterday was 21 degrees. And we're going to say Superman travels 180 kilometers. So that's 25 degrees west. Okay, I'll get out of the way right now. This should take not too long. I'll pause the video and we'll come back with the solutions for that. Okay, there's some that will be a little bit counterintuitive here. All right, so if you think if it's possible, if it has a direction, then we can write it as a vector. If not, then it'll be a scalar. I apologize. I'm going to pause this. Hopefully everyone can see. Sorry.